Usually when we look at a garden, there's this underlying expectation of simple, tidy categories.
Right, like a grocery store aisle.
Exactly. It's almost like walking down the aisle of a grocery store. You see a tomato plant, your brain immediately thinks salad.
Yeah. Or you see a rose bush, you think bouquet.
Right. We just mentally file everything away as straightforward, safe, and, distinctly categorized.
It is a comforting way to view the world, honestly. I mean, we inherently want nature to be predictable.
We do.
We want it to fit neatly into these little conceptual boxes we build for it. Food goes in one box, poison goes in another, medicine in a third.
But then you step out of that curated garden and into the world of complex botanical chemistry.
Oh, yeah. That's where it gets messy.
Specifically, the wilder, unmanicured edges of the carrot family. And suddenly those little boxes just completely disintegrate.
They absolutely fall apart.
We find ourselves looking at a botanical landscape that is just full of terrifying, beautiful paradoxes.
Mm-hmm.
A landscape where the line between, like, a miracle cure and a deadly weapon is microscopic.
That is where the natural world stops being a grocery store and starts acting like a highly sophisticated, deeply unpredictable chemical laboratory.
And that is exactly where we're taking you today. Because today's mission is to completely deconstruct a single, seemingly ordinary botanical family.
A family that secretly influences absolutely everything around us.
Right. We are talking about medieval magic, highly exclusive modern cocktails, multi-million-dollar luxury perfumes, excruciating skin disorders, and
an incredible cutting-edge cancer research.
It's just a staggering spectrum of influence for one group of plants to hold over human history and modern science.
It really is. It's almost hard to believe.
And to guide you through this deep dive, we've assembled a truly eclectic stack of sources.
We're not just going to read you a bibliography, though.
No, we're going to weave these directly into our conversation. We'll be pulling from botanical databases, specifically Plants for a Future, and the North Carolina Extension Gardener.
We're also going to unpack the wildly chaotic Wikipedia history of Chartreuse liqueur.
Which is a wild ride.
Yeah.
And we'll dive into a dense medical overview of phytophotodermatitis from Medscape.
Along with dissecting a pharmacological paper from the Journal of Food and Drug Analysis looking at grapefruit furocoumarins.
We're even analyzing a literal U.S. patent on musk fragrance enhancers.
Plus an ecological report from the Ecological Society of America.
And finally, chemical breakdowns of essential oils from the Tincture and Press archives.
The goal here is to connect the dots between history, chemistry, ecology, and medicine.
Exactly. We want to show you the underlying mechanisms of these plants, proving that nature is the ultimate paradoxical master chemist.
So we have a lot of ground to cover.
Okay, let's unpack this.
Yeah.
Let's start by painting a vivid picture of the plant sitting at the very center of this massive web.
Right, the star of the show.
We are talking about Angelica Archangelica. When you're looking through the North Carolina Extension Gardener database, I realized very quickly that this is not some delicate, fragile little flower you'd press into a book.
Oh, no. Not at all.
This is a robust biennial, or sometimes a short-lived perennial, belonging to the Apiaceae family.
Which is the broader carrot and parsley family, for context.
And it is an absolute giant. We are talking about stalks that can grow up to 7 feet tall.
Yeah, 7 feet is a towering presence for an herbaceous plant. Visually, it completely dominates its space.
I can imagine.
It features these stout, fluted, bright green stems that are entirely hollow inside, sometimes tinged with a deep purple hue at the base.
And the leaves are massive too, right?
Huge, sometimes reaching up to 3 feet long at the bottom of the plant.
Right.
And they're divided into these complex, finely toothed leaflets.
And then at the very top of those towering stalks, usually in its second year of life, it produces these large, semicircular double umbels.
Right, yellowish white or greenish flowers.
I want to make sure we visualize that umbel correctly, though. It's basically a cluster of tiny flowers that all sprout from a common center point on short stalks, right?
Exactly.
Sort of spreading out to look like an inside-out umbrella.
That is a highly accurate way to picture it, yeah. The stems radiate outward from a central point, creating a wide, flat, or slightly curved landing pad of tiny blooms.
Okay, got it.
And beyond its visual dominance, Angelica Archangelica has a heavy, undeniable atmospheric presence.
The sources note it emits a strong, complex, musky odor.
Yes, and it carries a warm, aromatic, sweet taste that very closely resembles licorice.
It's a plant that prefers cool climates, thriving in damp, marshy areas.
Often growing wild right alongside running rivers and streams.
Now, what really caught my attention in the Plants for a Future database is that practically the entire plant is edible.
Which is surprising, right?
Yeah, it feels really rare for something that looks so alien and imposing. But the roots, the seeds, the leaves, and the stems have all been utilized in culinary traditions for centuries.
The stalks can actually be peeled and eaten raw, almost exactly like you would eat a stick of celery.
But what is truly wild to me is that they were frequently candied.
Yes. Candied angelica stems are a classic, very old-school confectionery technique.
How does that even work?
Well, they would boil the stems, steep them in heavy sugar syrups over several days, and then dry them out.
Wow.
The result was these bright green, incredibly sweet, licorice-flavored decorations. They were used on puddings, trifles, and heavy fruitcakes.
So in a historical culinary context, you can think of it acting much like a medieval rhubarb.
That's a great comparison, but the people of the Middle Ages weren't just using this as a sweet garnish.
No, definitely not.
Right.
The very botanical name itself, Archangelica, carries some incredibly heavy historical and theological weight.
What's fascinating here is the sheer level of reverence medieval society held for this specific plant.
It wasn't just a helpful herb.
No, it was viewed as a miraculous divine intervention. Folklore dictated that an archangel actually descended from heaven for the express purpose of revealing the plant's medicinal qualities.
Most accounts cite either the Archangel Michael or Raphael, right?
Exactly. Revealing it to mankind during a time of crisis.
I mean, you literally do not get a higher product endorsement in medieval Europe than an archangel hand-delivering it from heaven.
You really don't, and because of that divine association, its perceived power was absolute.
It was believed to actively ward off evil spirits and counteract malicious spells.
More practically, it was viewed as a premier defense against contagions, particularly the bubonic plague.
People would chew the dried roots, wear pieces of it around their necks.
Or burn it in their homes to purify the air. Yeah. It was also highly prized for treating severe digestive disorders, purifying the blood, and neutralizing poisons.
It was the absolute foundational apothecary herb of the era.
It really was.
But I want to push back on this a little bit, or at least point out a terrifying detail I noticed in the botanical sources that complicates this whole divine cure-all narrative.
Oh, I think I know where you're going with this.
We have this angelic plant that you can allegedly just chop up, candy, and sugar and eat like celery. But the North Carolina Extension Gardener source explicitly warns that Angelica Archangelica visually resembles Conium maculatum.
Ah, yes. Conium maculatum is poison hemlock.
Poison hemlock, the exact plant that famously killed the philosopher Socrates.
The very same.
I am looking at pictures of both, and I am genuinely struggling to tell them apart. How is it that a plant considered so uniquely angelic and profoundly edible looks almost identical to one of the most deadly neurotoxins in the natural world?
It's a dangerous game. Foragers back then and even today must be walking a razor-thin line.
So true.
If we connect this to the bigger picture of botanical evolution, particularly within the Apiaceae family, visual mimicry and parallel evolution are incredibly common.
So they just naturally end up looking alike.
Yeah, both Angelica and poison hemlock feature those tall, hollow stalks. Both feature those feathery, fern-like leaves.
And both produce those wide, umbrella-like clusters of tiny white or greenish flowers.
Exactly. To the untrained eye, the Archangel of Healing and the Ultimate Executioner look nearly identical.
So if I am a medieval peasant foraging by a stream, and I accidentally grab the hemlock instead of the Angelica, what actually happens to me?
The mechanism of poison hemlock is brutal. It contains an alkaloid called conine.
Conine, okay.
Unlike the medicinal compounds in Angelica, conine is a powerful neurotoxin that directly disrupts the workings of your central nervous system.
Oh, man.
It binds to your nicotinic receptors, causing an ascending muscular paralysis.
Ascending meaning it starts at the bottom.
Right. It starts in your feet and legs, moving upward until it eventually paralyzes the respiratory muscles.
That's horrifying.
And the worst part is, your mind remains completely clear and awake while your body stops being able to breathe.
That is horrifying. And they look exactly the same.
Identical to the untrained eye.
It really drives home why absolute 100% positive identification is required before consuming anything harvested from the wild.
Nature hides its most potent, complex, and deadly chemicals behind very deceptive, uniform appearances.
It raises an important question about how our ancestors learned to differentiate these plants.
likely through a very grim process of trial and error.
Yeah, unfortunately.
Over generations, they learned to identify the subtle differences, like the purple spotting on the hemlock stem.
Or the specific odor of the crushed leaves, the exact shape of the seed pods.
Exactly.
And once they successfully identified that potent, safe chemistry within Angelica, humans spent centuries trying to harvest and perfect it.
Which brings us to one of the most incredible historical narratives in our source stack.
Oh, I love this part. No one harvested and manipulated the complex chemistry of Angelica, quite like a highly secretive order of silent monks in France.
We are moving from the damp, muddy banks of medieval streams into the silent, stone-vaulted cellars of the Carthusian monks.
Let's talk about Chartreuse. Based on the Wikipedia history provided in our sources, Chartreuse is this incredibly vibrant, herbaceous French liqueur.
And the origin story reads less like culinary history and more like a geopolitical thriller.
It really does. The story kicks off in the year 1605. A marshal of artillery to the French King Henry IV, a man named François Annibal d'Estrées, travels to the Carthusian monks at a monastery in Vauvert near Paris.
And he presents them with a mysterious alchemical manuscript.
Just hands it over.
We have to understand what an alchemical manuscript represented in 1605. It wasn't just a recipe card.
Right.
It was a dense, highly coded text combining early chemistry, botany, and philosophy.
This specific manuscript supposedly contained the complex formula for an elixir of long life.
What's fascinating is that the recipe was so overwhelmingly intricate, involving so many rare ingredients and precise chemical processes.
So complex that the monks didn't even attempt to fully decode and master it for over a century.
130 years just sitting on a shelf.
Just gathering dust.
It wasn't until 1737 that a specific monk, Brother Jerome Maubec, dedicated himself to deeply studying the text.
He managed to untangle the ancient terminology, source the botanicals, and significantly enhance the original recipe.
Yes, to create what became known as the elixir végétal de la grande Chartreuse.
And this is where our towering friend, the Angelica plant, comes roaring back into the spotlight.
The Chartreuse formula is famously secretive, but it is known to contain 130 different herbs, plants, roots, and flowers.
All meticulously macerated in a high-proof wine alcohol base.
While the exact proportions are a closely guarded secret to this day, older historical texts give us clues.
Right, like a 1900 hotel steward book mentioned in the sources. It lists Angelica roots and seeds as a massive foundational component of the liqueur's unique flavor profile.
It sits right alongside things like cinnamon, mace, lemon balm, hyssop, peppermint, and thyme.
So when you taste Chartreuse, that underlying earthy, bittersweet licorice and musk note that anchors the entire chaotic bouquet of 130 plants.
That relies incredibly heavily on the complex chemical extraction of the Angelica plant.
But what is truly staggering about Chartreuse isn't just the sheer botanical complexity of balancing 130 different ingredients.
It's the survival of the recipe itself through immense, violent, historical upheaval.
I was reading this timeline and my jaw kept dropping. The monks were violently expelled from France during the French Revolution in 1793.
The monastery was seized, and the manufacture of the liqueur stopped entirely.
A working copy of the manuscript was kept hidden at the monastery, but the original priceless manuscript left with a monk who was subsequently arrested by revolutionaries.
While he was in prison, he managed to secretly pass it to a friend outside.
That friend thought the Carthusian order was destroyed for good, so he turned around and sold the manuscript to a local pharmacist in Grenoble.
So the recipe basically becomes a piece of commercial property.
Right. And then the political landscape shifts again.
In 1810, Emperor Napoleon Bonaparte issues a decree demanding that all secret medical recipes and remedies in the empire be sent to the Ministry of Interior in Paris.
He wanted them for review and state control.
Napoleon essentially wanted to nationalize all intellectual property related to medicine.
So the Grenoble pharmacist dutifully sends the Chartreuse manuscript to Paris.
But incredibly, after reviewing this ancient, hyper-complex alchemical text for an elixir of long life,
The government officials stamp it refused and send it back.
they deemed it not a valuable state secret, but rather a well-known, perhaps overly complicated and useless folk remedy.
It survived Napoleon's imperial bureaucracy because the bureaucrats thought it was too complicated to bother with.
Exactly. Eventually, the pharmacist dies, and his heirs, clearly not knowing what to do with it, return the manuscript to the Carthusian monks.
Who had finally been allowed to return to their monastery in 1816.
But the friction between the monks and the French state doesn't end there.
No, it doesn't. Nearly a century later, in 1903, The French government passes laws against religious associations and expels the monks yet again.
The government aggressively confiscates their entire distillery, their equipment, and their trademarks.
The monks are forced to flee the country, eventually settling in Tarragona, Spain.
There, they quietly set up a new distillery and continued to make the authentic liqueur under a different label.
Tarragona, using their secret knowledge.
Meanwhile, back in France, a state-backed corporation takes over the confiscated monastery and the original copper stills.
And they try to produce and sell Chartreuse themselves.
They have the brand name, they have the equipment, they have the location.
But there is one massive problem.
They do not have the recipe.
They didn't know how to balance the 130 botanicals.
They didn't know the specific maceration times or the distillation temperatures.
The state-backed knockoff was universally recognized as inferior, and it failed miserably on the market.
The corporation eventually went completely bankrupt.
And following the bankruptcy, a group of local French businessmen quietly bought up all the failing corporation's shares and trademarks.
And they gifted them back to the monks in Spain, allowing them to eventually return to France.
They even survived a massive geological disaster. In 1935, a catastrophic mudslide completely destroyed their newly rebuilt distillery in France.
It was so devastating that the French army actually had to be called in to help the monks excavate
And rebuild the operation in a safer location nearby. The fact that we can drink this today is a statistical miracle.
Let's look at the modern versions of this surviving elixir because the sources detail a few distinct variations.
You have green Chartreuse, which was formulated in 1840. This is the heavy hitter.
It is a potent 110 proof, which is 55% alcohol by volume.
And what's amazing is that it gets its brilliant, almost glowing green color entirely naturally from a final proprietary maceration of plants.
Right, there are absolutely no artificial dyes or colorants used.
Then you have yellow Chartreuse, also developed around 1840. It is a bit milder, sitting at 86 proof.
It is noticeably sweeter, and according to that 1900 Steward book we mentioned, it builds upon the foundational green recipe.
But it heavily incorporates additional botanicals like cardamom seeds and saucotrine aloes.
To achieve that distinct golden yellow hue and a much softer, more honeyed flavor profile.
And for the true collectors, there are the VEP versions, Vieillissement Exceptionnellement Prolongé.
Which translates to exceptionally prolonged aging.
They take the green or yellow formulas and age them for years in massive oak casks, mellowing out the volatile compounds.
Creating this impossibly smooth texture.
Now, to put all of this ancient history into a modern context, Chartreuse today has become the ultimate holy grail for the modern mixology movement.
The cultural shift regarding this liqueur over the last 20 years is fascinating.
During the early 2000s craft cocktail renaissance, forgotten pre-prohibition drinks like The Last Word exploded in global popularity.
A drink which relies completely on the sharp herbal punch of green chartreuse to balance gin, maraschino liqueur, and lime juice.
Suddenly, high-end cocktail bars couldn't operate without it. But it was the global COVID-19 pandemic that truly shattered the supply chain.
Exactly. When the lockdowns hit, everyone was stuck inside, trying to become a master bartender in their own kitchen to pass the time.
The demand for Chartreuse literally doubled worldwide seemingly overnight. By 2022, global sales were hitting over $30 million.
Every bar, every high-end liquor store, every home enthusiast was clamoring for more bottles.
So you have this massive, unprecedented global demand. There are tens of millions of dollars sitting on the table just waiting to be claimed by simply running the stills longer.
And I look at this from a business perspective, and the next step is obvious. You scale up production.
How do the monks respond?
They responded in a way that completely defies every metric of modern capitalist logic.
Which is so refreshing.
In 2019, seeing this massive upward trajectory in a man, the Carthusian monks proactively decided to institute a strict cap on their global production.
They limited themselves to producing exactly 1.6 million bottles a year.
And explicitly stated they would not produce a single drop more, regardless of demand.
They just looked at a booming global market and said, nope, we are done growing. Why?
They cited two profound reasons. First, the environmental reality. Foraging, harvesting, and processing that sheer volume of 130 different botanicals from the surrounding mountains was becoming ecologically unsustainable.
They recognized they were pushing the local environment past its breaking point.
Second, and fundamentally more important to them, they remembered who they are. They are Carthusian monks.
Right.
Their primary sworn mission in life is not to act as global liquor executives managing a scaling multinational supply chain.
Their mission is a life of deep solitude, silence, and prayer.
They felt that the constant screaming demands of managing this massive business were actively pulling them away from their spiritual vocation.
I genuinely respect that so much. But the result is that right now there are massive global shortages.
Bartenders are hoarding bottles in their cellars. Liquor stores have waiting lists for a bottle of green Chartreuse.
And to think that intensely alluring, bittersweet, licorice musk flavor that makes the liqueur so addictive.
That specific flavor profile that makes people scour the earth and pay massive markups for a single bottle.
It all relies so heavily on the humble, deceptive Angelica root we started with.
It does, but we need to examine that root closer.
Because while the flavor of Angelica is deeply entwined with culinary history and silent monks, that specific musk note you just mentioned isn't just for drinking.
No, it is a highly coveted multi-million-dollar asset in an entirely different industry.
The world of luxury fragrance.
Here's where it gets really interesting.
We are shifting our focus from how this plant tastes to the physics of how it smells.
And for this, we are looking at an incredibly dense document, U.S. Patent 600-8185A, along with detailed chemical analyses from the tincture and press source.
The scent profile of the Angelica root is heavily defined by a very specific class of chemicals called macrocyclic lactones.
I'm going to need you to break that term down for me, because it sounds like something out of a synthetic chemistry lab, not a damp weed growing by a river.
Well, let's look at the mechanics of it. Macrocyclic simply means a very large, closed ring of atoms.
Okay, a big ring.
A lactone is a specific type of organic ester built into that ring. So macrocyclic lactones are essentially large, heavy, ring-shaped molecules.
The specific one we are most interested in from the Angelica root is called 15-pentadecanolide.
In the commercial fragrance industry, it is widely known by its trade name, exaltalide.
Now, why does the global perfume industry care so deeply about this one specific microscopic ring of atoms?
It's not just because it smells pleasant, though it does have a very sweet, warm, powdery musk aroma.
They care because of its functional physics.
The alchemy source breaks this down beautifully. 15-pentadecanolide is crucial because it acts as what perfumers call a fixative.
When you spray a high-end perfume, you have all these highly volatile compounds with the very light, delicate citrus, mint, or floral notes.
Because they are light molecules, they have a high vapor pressure. The moment they hit the warmth of your human skin, they want to immediately evaporate into the air.
If you just sprayed those floral notes, the perfume would vanish in 10 minutes.
A heavy, fixative molecule like this macrocyclic lactone essentially acts like a molecular anchor.
It physically interacts with those lighter, volatile molecules, holding onto them and significantly slowing down their rate of evaporation.
It binds the entire perfume to your skin, so the scent lasts for 8 hours instead of 8 minutes.
That's the core of it. It is a non-reactive carrier.
It stabilizes the entire complex formula without chemically reacting with, and therefore destroying, the other delicate floral or woodsy structures in the perfume.
The patent we are looking at explicitly outlines how master perfumers rely on these lactones for two very specific artistic functions.
First, it provides what they call intensity of the initial scent.
When you first spray the perfume and inhale, the lactone gives that immediate, powerful, voluminous punch to the olfactory system. It pushes the scent outward.
And second, it provides a crucial function called rounding off.
I love that term, rounding off.
I imagine it like an audio engineer mixing a song. The patent describes rounding off as ensuring no single sharp fragrance note awkwardly stands out and overpowers the rest of the bouquet.
The lactone acts like a botanical blender. It smooths out the rough edges of the 50 different ingredients, so they all harmonize perfectly into one unified scent profile.
But the chemistry of Angelica's scent gets even more nuanced and, frankly, much stranger than just that one molecule.
The tincture and press source dives into a mind-bending chemical reality regarding a physical concept called chirality.
And they look specifically at another molecule found in the root, 12-methyl-13-tриdecanolide.
Okay, I have heard the term chirality before, but I always get it jumbled. Let's explain this clearly.
It's basically the idea of handedness in molecules, right? Like your left and right hands.
They are exact mirror images of each other.
They're made of the exact same parts. 4 fingers, 1 thumb, a palm. But no matter how you turn them, you cannot perfectly superimpose your left hand over your right hand facing the same way.
That is the absolute best way to visualize it. In organic chemistry, these mirror image molecules are called enantiomers.
They possess the exact same chemical formula.
They have the exact same number of carbon, hydrogen, and oxygen atoms connected in the exact same sequence.
But their three-dimensional orientation in physical space is mirrored.
Usually, chemists designate one as the R form, from rectus, right, and the other as the S form, from sinister, left.
And this is where it completely blows my mind, because your physical nose can tell the difference.
According to the chemical breakdown in the sources, the Angelica plant naturally synthesizes both enantiomers of 12-methyl-13-tridecanolide.
And it produces them in a very specific, consistent ratio. About 72% of the 12R version and 28% of the 12S version.
The dominant 12R version smells incredible.
It is described as a beautiful, clean, transparent musk with distinct hints of sandalwood and fresh pear.
But its mirror image, the 12S version, which is sitting right next to it in the exact same root, made of the exact same atoms,
Has a completely divergent olfactory profile. It smells heavily animalic.
it has strong, camphoraceous, earthy, and distinctly sweaty bodily aspects.
It is a much darker, dirtier, more primal smell.
It's the exact same atoms, just arranged backward in three-dimensional space, and one smells like a crisp pear, and the other smells like gym sweat.
Nature is just showing off at this point. How does our nose even know?
It highlights the profound mechanical precision of human olfactory receptors. Smell isn't just about what atoms are present.
It is a physical lock-and-key mechanism.
The receptors inside your nose are complex 3D folded proteins. The 12R molecule physically fits into certain receptor pockets perfectly, triggering a signal to your brain that says pear.
The mirrored 12S molecule physically cannot fit into that same pocket, just like your left hand won't fit into a right-handed glove.
Instead, it slides into a different receptor entirely, which sends a signal to your brain saying sweat.
Our noses are sensitive enough to detect the spatial orientation of a single methyl group attached to a microscopic ring of carbon atoms.
And humans have figured out a brilliantly low-tech, patient way to maximize this scent extraction.
The sources note a specific study on how post-harvest storage affects the chemical makeup of these roots.
If you take fresh Angelica roots, crush them up to break down the cell walls, and just let them sit in storage for about 2.5 months, something amazing happens.
The lighter, sharper, more pine-like scent molecules, things like alpha pine, simply evaporate into the ambient air over time.
But those heavy, valuable, ring-shaped musk lactones don't just stay put.
Their relative concentration within the remaining oil actually increases by 2 to 5 times.
It is a process of natural passive concentration.
By simply waiting, you allow the plant material to shed its highly volatile compounds.
The volume of the oil decreases, but what is left behind is a vastly richer, denser, much more potent concentration of the highly prized fixatives that the perfume industry desires.
So we have this towering plant meticulously creating these beautiful, heavenly musk lactones.
It serves as the foundational backbone for high-end luxury perfumes and the secret liqueurs of silent monks.
But, as we hinted at in the very beginning when we compared it to poison hemlock, this plant has a profoundly dark side.
Because while it is utilizing energy to synthesize those gorgeous macrocyclic lactones to hold on to scent,
It is simultaneously manufacturing a completely different, deeply sinister class of chemicals for a very different purpose.
and this brings us to the internal defensive weaponry of the Apiaceae family, furocoumarins.
This is where we transition into the deeply unsettling medical data from the Medscape overview.
We are talking about a medical condition called phytophotodermatitis, or PPD.
The name itself is a mouthful, but if we break it down, it's very logical. Phyto meaning plant, photo meaning light, and dermatitis meaning severe skin inflammation.
It is clinically defined as a cutaneous phototoxic inflammatory eruption.
We need to look closely at exactly how this happens because it is essentially a highly sophisticated chemical booby trap set by the plant to punish anything that damages it.
This reaction occurs when a person's bare skin comes into contact with the sap containing phototoxicity.
Now, what's crucial to understand is that, as the sources note, these chemicals are not just found in the wild Angelica plant.
No, they are abundant in everyday grocery items within the same botanical family, like celery and parsnips, as well as in figs, and very notably in citrus fruits like limes.
Yes, this is the infamous margarita dermatitis or Club Med dermatitis you hear horror stories about.
When people squeeze massive amounts of fresh limes for cocktails while sitting on a sunny beach.
That is the exact scenario. The trap is physically set when the furocoumarin-rich oil gets onto the surface of your skin.
But the trap isn't sprung immediately. You can have the oil on you and feel absolutely nothing.
The trap is only activated when that specific patch of skin is exposed to a very specific environmental trigger.
Long-wave UVA radiation, specifically within the 320 to 400 nanometer wavelength range, which is abundantly present in natural, unfiltered sunlight.
So I touch the crushed Angelica plant while foraging, or I get lime juice all over my hands, and nothing happens.
Right.
I wash my hands with water, maybe I don't get all the oil off, and I feel fine, but then I walk out into the direct afternoon sun.
And that's when it starts.
I am struggling to understand how light, just normal sunlight, actually triggers a severe chemical burn. What is the physics here?
Let's look at the mechanics of the light interaction. A ray of sunlight isn't just brightness.
It's a stream of photons, each carrying a specific packet of energy.
When a photon of UVA light strikes the furocoumarin molecule resting on your skin, the molecule actually absorbs that photon's energy.
This sudden influx of energy physically alters the molecule.
It excites it from its normal, stable ground state into what quantum chemistry calls a triplet excited state.
Think of it like tightly winding up the spring on a jack-in-the-box.
The molecule becomes hyper-energized and violently reactive.
The Medscape overview explicitly details that once in this excited state, two distinct catastrophic photochemical reactions occur simultaneously within your skin cells.
Okay, walk me through the cellular catastrophe. Let's look at the type I reaction first. What is the energized molecule doing?
The type I reaction is oxygen independent. The hyperexcited furocoumarin molecule penetrates the nucleus of your human skin cell.
And physically intercalates, meaning it wedges itself into your DNA.
Imagine the DNA double helix as a twisted ladder.
The furocoumarin physically inserts itself between the rungs of the ladder, specifically targeting the pyrimidine bases, which are thymine and cytosine.
Once wedged in there, it forms rigid, covalent chemical bonds with both sides of the ladder, creating what's called a crosslink.
It's basically using the energy from the sun to staple the two strands of my DNA double helix together so they can't come apart.
That is exactly what happens. When that skin cell naturally tries to divide and replicate during mitosis, it needs to unzip its DNA to copy it.
But it can't. The DNA is stapled shut.
The cellular machinery crashes, the cell realizes its core blueprint is catastrophically damaged, and it stops functioning entirely. That is type 1.
Now, the type 2 reaction occurs at the exact same time, but it is oxygen dependent.
The excited furocoumarin molecule transfers its excess solar energy directly to ambient oxygen molecules floating within the cellular tissue.
This massive energy transfer creates highly volatile reactive oxygen species, also known as free radicals.
So if type Y is stapling the DNA shut, what are the free radicals doing in type 2?
The free radicals act like microscopic shrapnel. They violently tear through the lipid bilayer that makes up the cell membrane.
They blow holes in the outer wall of the cell.
This causes massive edema, meaning fluid rushes in and the cell swells.
Furthermore, this membrane destruction aggressively activates the arachidonic acid pathways,
which are the body's massive drivers of severe inflammation.
So type I is quietly destroying the software inside the nucleus, the DNA, and type 2 is violently blowing up the hardware, the cell membrane.
The inevitable result of both of these occurring simultaneously is total cellular catastrophe,
leading to apoptosis, which is the medical term for programmed cell death.
And the clinical manifestation of tens of thousands of your skin cells suddenly undergoing synchronized apoptosis is agonizing.
The medical sources paint a vivid, honestly terrifying clinical picture. You get this plant juice on you, you go into the sun.
About 24 hours later, a burning erythema appears, which is intense, angry redness, and deep pain.
By 48 to 72 hours, agonizing, fluid-filled bullae, massive blisters begin to form.
But the most bizarre and diagnostic part of PPD is the physical shape of the blisters.
Because this cellular destruction only happens in the exact microscopic locations where the chemical touched the skin and the UV light hit it.
The blisters form in perfect, unnatural geometric shapes.
You'll see a perfectly straight, linear drip running down a forearm where a drop of juice rolled.
Or, horrifyingly, the exact shape of a handprint on a leg.
And the trauma doesn't end when the painful blisters finally pop and heal weeks later.
The blistering is almost always followed by severe post-inflammatory hyperpigmentation.
As the skin cells are violently destroyed by the reactions we just described, the melanin pigment stored inside them spills out.
And drops deeper into the dermis layer of the skin.
There, it is consumed by scavenger immune cells called melanophages.
These engorged melanophages essentially get stuck in the deep tissue, leaving dark, brown, irregular stains on the skin that look like permanent bruises.
These stains can last for months, or in severe cases, years.
Okay, I have to stop and ask a clarifying question here because I think a lot of people listening might confuse this reaction with something more common, like poison ivy.
Right.
But the Medscape source is incredibly explicit. Phytophotodermatitis is entirely independent of the human immune system.
It is not an allergic reaction.
You do not build up a tolerance to it over time, and you don't need any prior exposure to become sensitized.
It is a straight-up objective photochemical burn governed by physics, not biology.
It will happen to literally any human being on Earth, regardless of their immune system, if they meet the two criteria, sap plus sunlight.
Given that it operates like strict physics, and given how common the trigger plants are, celery, parsnips, limes, why is this misdiagnosed by doctors so often?
That is one of the most tragic and alarming realities highlighted in the medical literature.
Because it is independent of the immune system,
Yep.
and because there is that significant 24 to 48-hour delay before the sun exposure triggers the blistering.
Patients rarely connect the plant they touched on Saturday to the massive blisters that appear on Monday.
But the real tragedy lies in the visual pattern of the blisters.
As we noted, because it only burns where the oil transferred, it can form perfect, localized handprints.
Imagine a scenario where a parent is in the kitchen preparing a meal, chopping celery or squeezing limes. They get the furocoumarin-rich juice over their hands.
They walk outside to the backyard and affectionately grab their child's bare arm or leg to pull them away from a hazard.
The child then continues to play in the afternoon sun.
48 hours later, that child develops massive, agonizing, bruised-looking, blistering handprints, precisely where the parent grabbed them.
Oh my God.
Yes. The medical sources explicitly warn that PPD in children, specifically because of these perfect handprint patterns,
Is sometimes horrifyingly mistaken by well-meaning pediatricians, emergency room doctors, and social workers as direct physical evidence of child abuse.
Massive traumatic investigations into parents have been launched because neither the parents nor the physicians realized what they were looking at.
They didn't realize it was a delayed photochemical reaction from a weekend picnic.
That is absolutely devastating. A simple, total misunderstanding of complex plant chemistry leading to an unimaginable family nightmare.
It just violently underscores how potent, invisible, and unforgiving these defensive botanical chemicals are.
So let's step back and look at what we've learned about this plant's weaponry.
We have furocoumarins. They use the energy of sunlight to physically cross-link human DNA, blow apart cell membranes, and force our cells to commit mass apoptosis.
They are formidable, terrifying, microscopic weapons.
But it raises an incredible question. What if we didn't just stumble into these chemicals blindly on a sunny beach?
What if we could somehow harness that exact targeted cell-killing ability?
What if we could take this microscopic poison, bypass the chaotic environment of the skin, and purposefully deploy it inside the human body to fight our greatest internal enemies?
That profound pivot from poison to potential cure brings us directly to the pharmacological data.
Specifically, we are looking at the dense research paper from the Journal of Food and Drug Analysis, which examines grapefruit.
Grapefruit is a citrus cousin to Angelica, and it is rich in the exact same class of phyranocoumarins, specifically two highly active molecules called bergamotin and 6'7" dihydroxybergamotin.
Now, before we get to the miracle oncology cures, we have to talk about the most famous and sometimes dangerous medical interaction involving these specific chemicals,
which is universally known as the grapefruit juice effect.
Anyone who has ever been prescribed certain daily medications has almost certainly seen that bright yellow warning sticker plastered on the side of their pill bottle.
To not consume with grapefruit or grapefruit juice.
Yes, and the biochemical mechanism behind that warning sticker is a perfect example of how these molecules disrupt human systems.
When you ingest phyranocoumarins like bergamotin, they travel down into your digestive tract and eventually hit your liver and small intestine.
In those organs, they encounter a highly specific, vital enzyme called cytochrome P450, specifically the CYP3A4 variant.
You can think of this enzyme as the body's primary chemical disposal unit or a very strict bouncer.
Its entire job is to metabolize, meaning to break down and clear out foreign toxins and medications from your bloodstream.
But phyranocoumarins are what chemists call suicide inhibitors.
Bergamotin binds perfectly to the active site of that CYP3A4 enzyme and permanently disables it.
It completely shuts down the body's disposal unit.
Which means if you take a standard prescription medication, let's say a common statin to manage your cholesterol or certain powerful blood pressure medications,
And you wash that pill down with a glass of grapefruit juice.
the enzyme that is supposed to safely break down and filter that drug out of your system is out of commission.
The drug isn't metabolized. It just keeps circulating and building up in your bloodstream.
So taking one normal pill with grapefruit juice might suddenly act like you took 5 pills at once.
Potentially leading to a massive, toxic, accidental overdose from a correctly prescribed dose.
It creates a massive pharmacological traffic jam, all caused by the plant's natural defense mechanism.
But scientists looked at this interaction. They saw this incredibly potent, highly active class of molecules that could survive digestion and profoundly alter human enzymes and DNA.
So what does this all mean? They asked 2 questions. How exactly is the plant manufacturing these complex weapons from scratch?
And if it can kill cells and shut down enzymes so efficiently, can we aim that weapon at cancer?
I want to dig into that first question before we get to the cancer. How does a simple plant sitting in the dirt actually manufacture this complex furocoumarin weapon?
You are the expert here. I need you to translate this journal article for me.
Because it maps out the biosynthesis, and it looks less like biology and more like a high-tech robotic assembly line in an automotive factory.
A factory assembly line is the perfect way to visualize it. It is a highly orchestrated, multi-step enzymatic pathway where each enzyme acts as a robotic arm,
Making one highly specific modification to the molecule before passing it down the line.
The process starts with a very simple, standard amino acid called phenylalanine, which is common in all living things.
The plant first utilizes an enzyme called phenylalanine.
This enzyme's job is to deaminate the molecule. It aggressively strips away the nitrogen group.
The resulting molecule is tranexamic acid.
Okay, so step 1 on the assembly line, strip the nitrogen off the raw material. What's next?
The molecule moves down the line to the next enzyme, cinnamon 4-hydroxylase.
This enzyme forces an oxygen group onto the carbon ring, transforming it into perfumery acid.
Then, through a few more complex chemical steps involving silosterification and further hydroxylation,
The molecule is prepped for a critical, non-enzymatic structural shift called lactonization.
essentially the molecule structurally folds and bites its own tail, creating a closed double-ring structure.
This new double-ring molecule is called umbelliferone.
And umbelliferone is a big deal, right? That is the foundational base skeleton for all coumarins in nature.
Yes, umbelliferone is the parent molecule, but the plant isn't done.
To upgrade this into a phenocoumarin, the weaponized version, the plant brings in a heavy-duty enzyme called a prenyltransferase.
This enzyme takes a separate raw carbon chain and aggressively attaches it to the side of the umbelliferone double ring.
Finally, the plant uses its own internal cytochrome P450 enzymes to oxidize that newly attached carbon chain.
Forcing it to cyclize or loop back on itself, forming a third distinct ring, a furan ring.
In the moment that third ring closes, sorolin is born.
Sorolin, the exact, highly reactive molecule responsible for stapling human DNA shut and causing the massive skin blisters we talked about earlier.
Exactly. And from that sorolin base, the plant can make minor tweaks.
Adding hydroxyl and methyl groups to create bergiptin, or attaching a much longer geranyl carbon chain to create bergamotin.
The sheer complexity and energy the plant expends on this chemical engineering is a marvel of evolutionary biology.
Okay, so we understand the assembly line. We know exactly how the plant builds this weapon atom by atom.
Now, how are human scientists turning that weapon against cancer?
Because the speculation and extrapolation sections in these oncology studies are genuinely staggering.
We're talking about taking a blister-causing toxin and injecting it into tumors.
The in vitro research is revealing massive, unprecedented promise.
Because these phototoxicity are biologically designed to aggressively penetrate cells and disrupt core cellular machinery.
Researchers decided to test them against rapidly dividing aggressive cancer cells.
Let's look at the data on bergamotin first. Studies have shown that exposing breast cancer cells, specifically the highly aggressive, widely studied MDA-MB231 cell line, to bergamotin actively and significantly suppresses their proliferation.
Wait, how is it doing that? Is it just stapling the breast cancer DNA shut the same way it does to skin cells under UV light?
No, and that is what is so remarkable. It is attacking a completely different internal vulnerability.
Inside the dark environment of the body, without UV light to trigger the DNA cross-linking, bergamotin specifically targets and disrupts the STAT3 signaling pathway.
To understand why that matters, you have to understand STAT3. It is a messenger protein that regulates genes involved in cell growth and division.
In many aggressive cancers, the STAT3 pathway is broken. It is constantly turned on.
It acts like a broken telegraph, continuously sending the message, grow and divide, into the nucleus of the cancer cell, driving massive tumor growth.
Bergamottin chemically intercepts this process. It inhibits the activation of what's called the nuclear translocation of STAT3.
Let me translate that. It means the bergamottin acts like a chemical barricade.
It physically blocks the STAT3 messenger from ever crossing into the nucleus, the command center of the cell.
The cancer cell's command center stops receiving the signal to divide, so the tumor stops growing.
That is precisely how it functions. It effectively cuts the communication wire.
Furthermore, another furocoumarin we discussed, bergaptan, has been shown to induce estrogen receptor depletion in certain hormone-dependent breast cancer cells.
Actively removing another massive biological growth driver.
That is incredible. This is not just carpet bombing the tissue with poison. It is surgically dismantling the cancer cell's internal communication network.
And the paper mentions it is also being tested against multiple myeloma, which is a severe blood cancer, a type of leukemia.
Yes. In multiple myeloma cells, bergamottin demonstrated another unique mechanism.
It was shown to dramatically downregulate anti-apoptotic genes within the cancer cell.
Apoptosis. We're back to programmed cell death again.
Exactly. One of the main reasons cancer cells are so devastatingly difficult to kill is that they mutate to purposefully turn off their own internal self-destruct mechanism, apoptosis.
Normal cells know when to die if they're damaged. Cancer cells achieve a dark kind of immortality.
Bergamottin goes into the multiple myeloma cells and aggressively turns that self-destruct mechanism back on,
Actively forcing the leukemia cells to recognize their own mutations and die.
and beyond targeting existing cancers, if we return to the skin for a moment, bergamottin has been shown in laboratory models to actively block the DNA mutations initiated by certain severe environmental carcinogens.
It effectively acts as a preventative molecular shield against the initiation of skin cancer.
The paradox here is so thick you could cut it with a knife.
The exact same chemical class that absorbs sunlight to cause agonizing DNA stapling, blistering skin burns is being isolated in laboratories and researched to aggressively prevent skin cancer mutations internally.
It perfectly highlights the ultimate unbreakable rule of toxicology and pharmacology.
The chemical structure itself is neutral.
It is the dose, the environment, and the highly specific delivery method that determine whether a molecule acts as a deadly poison or a miraculous cure.
And if selectively dismantling breast cancer communication networks and forcing leukemia cells to self-destruct wasn't enough, the sources outline one more staggering medical application for these compounds.
Rebuilding human bone.
Yes. The research points to significant potential in treating osteoporosis.
Osteoporosis is a severe condition characterized by a dangerous loss of bone density, making bones incredibly brittle.
It is largely driven by a cellular imbalance between the cells that break down old bone tissue, called osteoclasts, and the cells responsible for building new bone tissue, called osteoblasts.
It's an imbalance between the body's demolition crew and the construction crew.
In osteoporosis, the demolition crew is working overtime, and the construction crew is asleep on the job.
And apparently bergaptan, one of our key Angelica furocoumarins, acts like a massive stimulant for the construction crew.
Strongly so. The pharmacological studies demonstrate that introducing bergaptan actively stimulates the proliferation and efficiency of osteoblasts.
It achieves this by directly upregulating the genetic expression of two critical factors: bone morphogenetic protein 2, or BMP2, and a key transcription factor known as RUNX2.
If the osteoblasts are the construction crew, upregulating BMP2 and RUNX2 is like flooding the construction site with highly detailed blueprints and massive work orders.
The cells suddenly know exactly where to build and are highly motivated to do it.
That analogy perfectly captures the mechanism.
In animal models designed to mimic the severe bone density loss of postmenopausal osteoporosis, the oral administration of isolated bergaptan significantly, measurably improved both overall bone mineral density
and the microstructural integrity of the trabecular bone network inside the limbs.
It offers a very real glimpse into a potential, highly effective, plant-derived future treatment for severe skeletal degradation.
Okay, I have to stop and just marvel at the absolute paradox we have unpacked over the last hour.
It's a lot to take in.
We are talking about a single, weirdly tall botanical family. It produces a root that silent French monks used to perfectly balance a $30 million historical liqueur.
It produces macrocyclic lactones that chemical perfumers use to anchor the most expensive luxury musks in the world to human skin.
Nature utilizes its furocoumarins to inflict third-degree, light-activated chemical burns on anyone who touches it.
And from those exact same toxic defensive chemicals, the brightest minds in oncology are finding mechanisms to stop breast cancer cells from migrating, force leukemia into remission, and rebuild the structural integrity of human bone.
The internal microscopic chemistry of this plant is astonishingly complex.
But its external life, out in the wild, interacting with the macroscopic world, holds one final massive surprise for us.
Yes, and to explore this final puzzle piece, we have to shift our lens from the microscopic world of targeted cellular biology back out into the macroscopic world of environmental ecology.
We are looking at a truly groundbreaking, paradigm-shifting study published by the Ecological Society of America.
Right. The report details the meticulous fieldwork of a researcher named Ko Mochizuki, operating out of the University of Tokyo.
He decided to dedicate his time to studying the specific ecological interactions of two native species in the Angelica genus, Angelica decursiva and Angelica heckenensis.
To truly understand why Mochizuki's published research is so groundbreaking, why it sent ripples through the botanical community, we first have to understand the long-held foundational ecological dogma regarding the entire Apiaceae family.
As we visualized at the beginning of our deep dive, these plants produce umbels, those large, flat, wide-open clusters of tiny white flowers.
From an evolutionary biology standpoint, producing an umbel is seen as implementing the ultimate open-door policy.
The plant's nectar is secreted right there on the flat surface of the flower. It is incredibly easily accessible.
It is not hidden deep within a complex tubular flower that requires a specialized long beak or a highly adapted moth tongue to reach.
Right. In all the ecology textbooks, plants with umbels are considered the ultimate generalists of the plant world.
The accepted academic assumption was that because the nectar is just sitting right there in the open, literally anyone passing by can stop in for a quick drink.
The textbooks taught that these plants cast the widest net possible, inviting over 100 different random insect species, tiny beetles, passing flies, small solitary bees, various butterflies,
to all share the nectar and passively pollinate the plant in return.
That was the widely accepted, unquestioned truth of the discipline. Generalist flower shape equals generalist pollination strategy.
But Mochizuki decided to actually sit down, ignore the textbooks, and meticulously observe these specific Angelica species in their actual wild habitat to see if the dogma held true.
He started his intense observation periods in 2015 deep in the Nagano Prefecture in Japan.
And continued them over years, culminating in highly controlled observations in 2018 at the Nikko Botanical Garden.
And the data he meticulously documented completely overturned decades of assumed ecological dogma.
Because he finally found out who was actually doing the pollinating.
And it wasn't a peaceful, diverse Disney movie collection of butterflies, beetles, and little bees sharing the nectar.
Not at all. He discovered, and statistically proved, that these specific Angelica species are pollinated predominantly by hornets.
Hornets. I absolutely love this visual.
It's like a neighborhood throwing a massive open invite block party. You set up the tables, you put out hundreds of little open cups of punch, and you expect the entire diverse town to show up and mingle.
But instead of the town showing up, a massive, intimidating, leather-clad biker gang rolls into the neighborhood.
They park their bikes, take over the entire street, surround the tables, and drink all the punch.
And they are so aggressive and terrifying that absolutely nobody else in the neighborhood even dares to walk down the street, let alone approach the table.
While it's an amusing analogy, biologically, it perfectly encapsulates the reality of the umbel.
Hornets are massive, highly aggressive, dominant apex predators of the insect world.
When a group of hornets occupies an Angelica inflorescence to fiercely feed on the easily accessible nectar, they physically dominate the space.
Any smaller, weaker insects, the bees, the butterflies, the flies, that attempt to land on the umbel are immediately driven away by aggression.
Or worse, they are actively hunted and preyed upon by the hornets, right there on the flower.
It's a hostile takeover of a flower. But why does this specific discovery matter so much to the broader scientific community?
Aside from providing a really cool, terrifying mental image of a hornet-covered celery stalk.
It matters deeply because it forces a massive reassessment of insect roles. Hornets are carnivorous predators.
They spend their days hunting other insects, butchering them, and carrying the protein-rich meat back to their nests to feed their growing larvae.
They are very rarely considered primary pollinators by ecologists.
The adults only drink floral nectar to get a quick sugar rush to fuel their incredibly energy-intensive flight muscles while they hunt.
Finding undeniable proof that an entire genus of plants might have evolved to rely predominantly on a highly specific, aggressively carnivorous apex predator for its sole reproductive survival.
Completely shatters the fundamental generalist assumption of the open flower.
It totally changes the conservation math on the ground.
Exactly. If you are a dedicated conservationist out in the field trying to protect a highly rare, medically valuable Angelica plant from extinction, the old textbook playbook told you something simple.
Just make sure the habitat is healthy enough to support a general mix of bugs. Any bugs will do the job.
But Mokizuki's new research violently corrects that. It says if you do not actively protect the specific aggressive hornet population within that localized ecosystem, this rare plant will inevitably go extinct.
Because the hornets are guarding the umbel, and absolutely nothing else is successfully pollinating it.
It highlights just how incredibly deeply entangled, specialized, and fragile ecological relationships can be.
Even within the life cycle of plants that science arrogantly assumed it completely understood a century ago.
It just proves that the closer and longer you look at this plant, the weirder, darker, and more wonderfully complex it becomes.
Which brings us to the end of our journey today.
Let's put this all together and synthesize exactly what we've unpacked.
We started by digging into the damp soils of the Middle Ages, looking at a towering celery-like cure-all root that peasants believed was hand-delivered by angels to cure the plague.
We tracked its sharp licorice flavor through the heavily guarded ancient alchemical manuscripts of silent Carthusian monks.
Watching the recipe survive the French Revolution, Napoleon's bureaucrats, Spanish exile, and catastrophic mudslides.
Only to become a modern $30 million a year mixology phenomenon, heavily rationed by the very monks who make it.
We unraveled the microscopic physics of its heavy chiral macrocyclic lactones.
Exploring how a mere shift in spatial geometry dictates whether a molecule smells like a crisp pear or gym sweat.
And how those molecules act as invisible anchors for the global luxury perfume industry.
We issued a stark, terrifying medical warning about its furocoumarins, detailing the exact light-activated quantum physics of phytophotodermatitis.
Where sunlight literally staples human DNA shut, causing agonizing burns and tragic misdiagnoses of child abuse.
But then we flipped the script, highlighting the incredible cutting-edge pharmacological potential of those exact same toxins.
To intentionally intercept STAT3 breast cancer communications, force immortal leukemia cells into apoptosis, and flood the body's construction crews with blueprints to rebuild postmenopausal bone.
And finally, we ended by overturning decades of established ecological dogma at a hornet-exclusive, hyper-aggressive botanical block party in the mountains of Japan.
It has been a massive journey, and it serves as a profound testament to the sheer chemical ingenuity and quiet, ruthless efficiency of the natural world.
But before we sign off, I want to leave you with one last, truly mind-bending concept derived directly from the margins of the source data we reviewed today.
We spent this entire hour talking primarily about the profound effects of just a tiny handful of isolated furocoumarins.
We focus heavily on molecules like sorlin, bergaptan, and bergamotin.
But the chemical papers noted a staggering, almost incomprehensible statistic.
Over 1,300 entirely different coumarin structures have already been identified, occurring naturally in the wild.
And new, highly complex variations are being discovered by botanists every single year.
1,300 different variations.
Yes, 1,300 variations of this incredibly potent chemical architecture.
So consider this. If humanity has managed to derive the historical magic of Chartreuse, the billion-dollar foundation of luxury perfumes, the agonizing molecular mechanics of deadly skin burns, and the absolute bleeding edge of targeted cancer therapies.
From just a tiny, localized handful of these molecules isolated within one specific plant family.
It raises the ultimate question.
What massive, undiscovered chemical revolutions, what unimaginable targeted medical cures, what incredible behavior-altering scents, or what terrifying, newly evolved toxins?
They're quietly sitting in the unassuming weeds of your own backyard right now.
Just waiting for the right frequency of light or the right hyper-specific scientific question to finally unlock them.
Imagine a massive, impenetrable locked safe. You look at it and it just looks like a simple green weed growing out of a crack in the sidewalk.
But inside, the blueprints for absolutely everything are just waiting in the dark.
Thank you for joining us on this deep dive into the source material. We hope we've completely ruined how you look at a simple garden. Stay insanely curious, keep asking the hard questions, and we will catch you on the next one.